Okay, so
you see everything correctly, right? And you hear me.
Yeah. Yeah. Okay, thanks everyone for coming. Then Riccardo is with us. He's doing his speech in the math department of Twente University. I was visiting their group and I had a marvelous time there. And we are hoping to we're working on something together. That is why I invited him to give this talk because like for us, it's very similar to what we were working. So Takayuki and Zahra are here. We are on the same team who were working on spatial networks and epidemics. We also have Lasse from the mass, who's also working more on mathematical sides. And the rest of people are basically network scientists working on different aspects. And I hope like we have a very enjoyable talk today. Anyway, Ricardo, let's get to business.
Yeah, thank you. Thank you for inviting me, for inviting me here. And well, even if it's online, but it's still nice to meet new people, also online. So today, I know not all of you have a very strong mathematical background, maybe. At least I was told to be soft on the mathematical side. So I try to really put a lot of visual stuff inside the slides. And so don't get scared if you see something too complicated. Hopefully there will be not such a thing, but anyway, everything will be shown together with some pictures. So hopefully everything will be clear. Today I will talk about this model that me and Maria Dayfen work together. It's a model that we call geometric random intersection graphs. Actually, these words are just a bunch of words that are put together. But hopefully, well, maybe you already encounter some similar model in your life, or maybe not. So I will just try to give you an introduction on what it is, and then we will see some properties of this model. And in this talk, what we will talk about is some motivation on this model that we are introducing. So why it makes sense to talk about this random geometric intersection graphs. We will look together at some other existing network models that were already there, and we will see some problems that we encountered when studies this model. We will give some precise definition. We see some properties. This asterisk here is just to tell you that this is where maybe things are going to be a little bit more technical, but yeah, don't be scared about this. Not too much technicalities in there. And then we will see some other interesting properties of this model. In particular, we look at percolation in this model. Probably percolation, I mean, we study percolation in the sense that we would like to check whether there is the emergence of an infinite component in the graph or not. So first of all, we will introduce the problem, and I will show you some results. There are also some proof ideas, but this is really only just a visual proof idea. It's no computation or anything else. So, okay, this said, let's start and let's see some motivation for this model. So I would like to start with this nice example. So we have some individuals spread around. In this case, I'm considering some kids. And these kids are, they have some geographical coordinates, and they also need to go to schools. And also schools have some geographical coordinates. So basically what happens is that some kids go to some schools. You see they connect, in this case, quite randomly to each school. Maybe one kid can go to more than one school, or something like this. But the real thing we are interested in is not this kind of network, but it's the connection that actually happen among students. And then to understand a little bit better this, we can just connect individuals that share the same school. So basically, you can imagine that this blue school, basically, it's what creates the ties in between these kids, this purple school as well, this green school as well. And then at the end of the day, we are left with a social network, which is basically a collection of different communities that are interacting among each other. We are interested in this kind of model. We're interested in this kind of networks, and we're trying to model this. And actually, what we are doing is considering a larger environment where basically the space can be infinite in size. So here we only see a smaller region of this space, where there are some individuals spread around, there are some groups spread around. Individuals are connecting to groups in some way that has to be defined by a proper model. And then we are just interested in the final result, which is the social network among the individuals. Okay, so, well, this looks easy. From a mathematical perspective, there are some things to do. So the first thing to do is to define properly this model. And to define this, we need to understand how the individuals are spread around, how the groups are spread around, and what is the connection between groups and individuals. So exactly how individuals are going to be connected to these groups. And what we're going to do, as we said, is studying some basic properties of this graph and to study the largest components of the outcome graph, so of this individual network. Okay, so let's see exactly the model, how it's going to be defined. But let's start first from some existing network models, and we start from this random intersection graph. So this is a very well-known graph in literature. It has been widely studied. This graph is basically a realization of what we did, or what we just said. So basically, we have a first group of vertices here. These are, you can consider this to be the individuals. And you have some other group of vertices down here. These are groups. And so you have these individuals connecting to groups somehow, right? And then at the end, you can just project onto the individual set, so onto this V set, and generate this projection graph. So you see, this random intersection graph is quite nice because we obtain exactly what we wanted. So we wanted to create some community structure induced by the fact that we are sharing, individuals are sharing the same group. But the problem of this model that was really widely studied, it is that there is no spatial embedding in this. So individuals do not have positions. And typically, this is something that you would like to have in a model because it is quite reasonable to assume that many existing real networks have some sort of spatial embedding, either that being a geographical coordinate or features or representation or something like that. And also another big problem here is that in this kind of networks, individuals rarely share more than one group. So for instance, you can see here, there are no groups that are shared by, so two individuals at most share one group, right? It's really rare that they can share more than one. And this is actually, this actually comes from the definition of this random intersection graph. And this, again, is a really bad thing, because in general, in real context, it may happen that two different individuals are going to visit more than one groups together, right? So maybe two kids can go to the same school, but they can also go to the same park. And this is not something that is represented by this model. So to, let's say, go a little bit farther, we can consider this other model that is already that was already existing, that is called a random connection model. In this case, you just grab your set of vertices, you put them, you put these nodes in a R2 or in whatever space that you like, and you basically connect these vertices if they are close enough. Actually, this connection may also not be indicator function of the fact of being close enough. So it can also be just a function of the two vertices. But the point is that it's a function that depends on the distance. So now this is a real spatial embedding of a network. We achieve typical observed properties, for instance, clustering, high clustering. The problem in this graph is that we don't have the intermediation of groups. And then in this case, the communities that are forming, like for instance, if you look at this region, you can sort of think this is a community, but this community is merely geometric. It has nothing to do with the fact that individuals are sharing the same group or they have they are visiting the same place or anything like that. It's more like a natural feature that is a inner feature that is possessed by the individuals. Okay, so the idea now is we have these two existing models. Let's try to merge them together and get something that is actually more realistic. And this is basically the idea behind the construction of the geometric random intersection graphs. And the idea is that you take individuals and groups, okay, you call them V and U, these vertex sets, and you distribute them accordingly to Poisson point processes on RD. So now the point is, I'm not really sure how many of you are familiar with Poisson point processes. So to just try to get you some insights of what is happening, I put here a definition first, but then we will show a picture of what a Poisson point process is. And the idea is that a Poisson point process, given an intensity function lambda of x, is a collection of points such that the number of points inside any region A, where A is, okay, technically speaking, should be a measurable set. So the number of Poisson point process of points in the process that are also in A are distributed accordingly to a Poisson random variable. This is a Poisson random variable. And the intensity is just the integral of the intensity function. So you compute this integral, you launch the random variable, and you see how many points you get in there. And this is a representation, for instance, of a Poisson point process. Here we have this intensity function, e to the minus x1 squared. We are on R2. We only have one coordinate, so the other coordinate is just constant equal 1. But so here we see that basically the number of the points are really well concentrating on the y-axis. And the idea is that if you take a region A and you compute the number of points inside of here, you just need to take this integral of this function inside the region, take a Poisson random variable, and you have the number of points that are inside of here. Maybe this is a little bit too technical, but in general, it's very easy. In general, when you consider especially homogeneous Poisson point processes, this is really easy because it looks like you take a fixed box and you randomly distribute points inside of it. So for instance, if the rate function was homogeneous, equal 1, this will be the picture you obtain. And of course, when lambda increases, when lambda increases, you have something like this. So you have more points, but they are still spread uniformly. Okay, so this set, this is the meaning of taking individuals and groups and spreading them as a Poisson point process. And you get two different intensities, lambda and mu. And these lambda and mu are, will play a very important role, so keep them in mind. And then you need to decide what is the connection between V and U, so any individual and any group. And you just assume that they connect with some probability given by this function G, a function of the distance, okay? And okay, there are some technical things you need to take into account. If you want to have a realistic model, you would like the function G to be radial, you would like it to be non-increasing. So you would like that two individual and group far apart are more unlikely to connect. Whereas if the group and the individual are close to each other, they should be more likely to connect, something like that. And also you need some non-degenerate condition, but that's again just some technicality. And at the end, this is what we get. So the individuals spread around and the group spread around, the bipartite version of the graph, and the projected version of the graph on the individuals. Here, just a small remark. Sometimes we consider the palm version. So the version of the Poisson point process where there is also one point on the origin. And this is not a hard assumption. Actually, it's something we can get for free. But that's the reason why sometimes you will hear me saying that we are considering the individual on the origin. And that's the reason why.
Sorry, can I ask one question?
Yeah, sure.
When you project there, you mean that you connect then whenever there's at least one common.
Yes, exactly. I'm not sure if you can see it from this picture, maybe. Let's see. Like you see this. Okay, wait. Laser. Okay, never mind. I don't know how to do this, but yeah, anytime, like for instance, this edge here is obtained because these two individuals are sharing the same group here. Yeah, so that's the projection, exactly. Okay, any other questions or?
And you do not allow like multi-links, right?
Sorry?
You do not allow multi-links. If two individuals
No.
share more than one group, it's again, the projection is always like a single.
Yes, exactly. Yeah, that could be a more general version to allow multi-links, but for our purposes, I mean, we only want to check whether individuals know each other, if they know each other, if they connect, and that's because basically they share at least one group. So yeah, we don't allow multi-edges. Okay, just very quickly, I want to show you the role of this connection function g of x. If you take different connection functions, so this is a indicator function of the distance to be smaller than 1, but these are other kind of connection functions. So this has exponential decay, this has a polynomial decay. If you take different g's, you obtain at the end a different global picture, of course. Just take into account the fact that here the number of edges that are in these three pictures are always the same. It looks like this is denser. It's more dense than the other two because, of course, you are allowing long edges to appear, but actually the number of edges is exactly the same. So the point is that unbounded support function G may allow very long connections appearing in the final graph. Okay, here I have some consideration on the edge probability, and actually I think we can just check this and then skip the rest because this is again a little bit technical, but the idea is that if we want to compute what is the probability that two individuals are gonna connect in the projection graph, so in the final picture, in the green picture, the idea is that we need to compute the probability that there exists a group such that in the bipartite version they were connecting, right? So we need to check whether this was the case or not. So whether this group U is connecting V1 and V2. And to compute this, again, there are some technicalities to deal with because we can actually compute what is the number of groups that are shared by V1 and V2. So N V1, V2 is the number of groups shared by V1 and V2. And the idea is that, okay, we need to compute what is this distribution now? What is the distribution of N V1, V2? And to do this, you start from the number of groups that were already present. And you can do a process that is called thinning. So instead of considering all these groups, you only consider the groups connected to V1. And what you obtain from this is a thinned Poisson point process that has this intensity. Something like this, you can do it again, and you can do it for the second vertex. You thin again the process, and you get a new Poisson point process. But what is this new Poisson point process? It gives you these remaining red groups. So it gives you the number, technically the groups that are connected to both vertices. And then you obtain what is the distribution of N, V1, V2, right? You actually observe that is some sort of self-convolution. I want really to skip this. It's an interesting, not interesting detail. But the point is that then you can actually compute what is the connection probability that in principle can be very ugly because it really depends a lot on the form of the function G. Remember, F is the self-convolution of G. And also from this, you can retrieve the fact that there is no edge independency. That means, assuming that this edge is present in the projection graph, is this edge independent from this one? And the answer is no. And the reason is that every time this edge is present, it means that there is some group appearing somewhere, and this group could be actually connected to these other two vertices. So yes, there is no edge independency, and actually this is going to be a big problem if you want to do mathematical analysis on this on this model, but unfortunately this is what we have. And like, for instance, if you want to compute the GRIGs, having no independency is a big problem because now the degree is just a sum of non-independent Bernoulli random variables. So it's quite hard to understand what is the degree distribution. Like, for instance, here I plot some the degree distribution for some choices of lambda, mu, and g. But the point is that they look similar to a Poisson distribution. This is the typical Poisson distribution shape, but it's not really a Poisson distribution, unfortunately. And here you can see other choices of lambda and mu, but again, this is slightly technical, maybe.
Small question.
Yes.
So you can power load with, you can probably tune G so that if you want to have a power load, you get it, or?
Yes, you can choose G to be a power law. Here I choose G to be a to have the exponential decay, but you can tune it to be a power law. Right? Was this the question?
What's the consequence of a power law G on the degree distribution?
Actually, I tried. It's not super different from this. So it will look a little bit more like a Poisson, but it's still not a Poisson. That's the only difference. But it's quite similar. I tried some simulation on this. I just did want to show this exponential decay because I feel like it's the most interesting, at least in my opinion. But yeah, power law decay will be very similar.
And can we do it in a reverse way, that given a desired degree distribution, can we tune G to obtain it? Or it's not necessary for work?
No, we cannot do it. And the reason is that usually, like for instance, you would like to have sometimes a heavy tail degree distribution, right? So for instance, you would like something like that. The problem is that we can show with some domination argument that even though we don't have the exact degree distribution, we can dominate it with something that is almost surely finite. And then sorry, with something that has almost surely an exponential decay, not almost surely finite. So the decay of the degree distribution cannot be whatever we like, unfortunately. To obtain some other prescribed degree distribution, the next step will be to assume that individuals or groups have some weight or some hidden variable or some hidden feature. And assuming this, we can maybe create some more popular individuals or something like this. And when you have this kind of feature, then of course you can recreate any prescribed degree distribution. If this was what you were asking.
Exactly.
But that's the next step, and it was not super clear to me and Mia how to generalize this, because something was done for similar models, but in this case it was not super easy to understand how to do it. Okay, just very quickly, I want to give you some results on percolation, because probably there is not much time left. And percolation, from how we define it, is just the existence of a component of infinite size in the projection graph. Why are we interested in the existence of an infinite size component? The reason is that we have an infinite size space. So we are using every time r to the power d, for instance, the plane R2. And we're interested if we can generate this infinite component size. The idea is that you want to compute what is the probability that the component containing vertex 0 is going to be infinite or not. And this probability is just some function of lambda, mu, and g, right? Because those are the only variables in our graph. And then we have some two different phases. We can have no percolation. We have no percolation when this probability is going to be 0, because then it means that it's impossible to have any infinite component size. And we have percolation when this probability is bigger than 0. This is because of 0-1 law, some probability stuff. So if you're not familiar with this, no problem. And the idea is that then if we fix the intensity of the individuals, we would like to check what is the intensity of groups that is needed to obtain percolation. And just to show it with some pictures, when lambda is fixed, equal 1, we want to check when we increase mu, if the final graph is going to create an infinite component or not. So somewhere in between 0.75 and 1, there should be this critical value, right? Of course, here you cannot see the infinite size component, but you can imagine that the global behavior is quite similar to this local behavior, and trust me. And then this is what we are interested in. And then we found some results on this. We found that basically the projection graph percolates whenever the bipartite version percolates. And also you can play with this and project onto the groups to the group vertices and see that that also percolates, but that's not a real point. That's not a real interesting thing. The interesting thing is that in any dimension bigger than 2, bigger or equal than 2, there is a different behavior depending on the fact that G has bounded support or not. So if G has not bounded support, then there is always a phase transition for percolation. So you have a critical mu, and you can have no percolation below, percolation above. But if you have bounded support, there is some regime in which there is no percolation phase at all. So you always have no percolation. And this means if there are too few individuals, basically you will not achieve percolation anyway. That's the point. Just to show you in a picture, if you have unbounded support, this is what happens. You have a curve distinguishing between the two phases. So here the blue region is where you have a very large big component. The largest component is very big. And here in the white region is where the largest component is very small. You can see that increasing mu, fixing lambda, so fixing a line and increasing mu, you will achieve percolation. So you will achieve a very large component. And when the support is bounded, this is not possible below some line, some threshold level. And that's basically the most important, interesting result that we got. Okay, I think I'm run out of time. So I will skip some proofs on these results for no percolation, that is basically involving some branching process domination. For the percolation phase, we have some coarse graining technique to couple our graph to a bone percolation, something like this. And when there is never percolation, this is just domination from some other existing model. And again, I skip the details, but this is the summary of this talk. And hopefully you got something insightful from this. You see that our model is basically a model for real-world networks where this kind of structure is happening. We get some close formula for the connection probability, but we have no edge independency, unfortunately. And we got this weird, but actually expected phenomenon on the persistent of the infinite component. Okay, so thank you for listening to this talk. Hopefully you liked it. And yeah, if you have any questions, I'm here.
Thank you. Chance?
Thank you for the great talk, first of all. You talked about this degree distribution of this graph, but do you have any results on for example, clustering coefficient or some kind of measure that characterizes how spatially embedded this network is?
Yeah, so we don't have it. Actually, I think that shouldn't be super hard to get. The idea is that when you compute clustering coefficient, you are also left with you're basically left with counting number of triangles. And the idea is that since your graph is spatially embedded, it shouldn't be too hard to at least dominate your graph with something smaller and prove that that smaller thing has a high clustering. Something like that. We didn't go through these computations because, well, also we didn't have much time, and we also thought, okay, it's more interesting maybe for us to just study percolation and explore that. But yeah, to us it seemed to be quite straightforward, and yeah, we didn't even do the computations. The reason why instead we focus on the GRIGs is that usually people really want to have a model where you can put the desired degree distribution.
Yes.
So yeah. Typically, I'm not sure about this, but at least in my field, we are not super interested to put the correct clustering coefficient into play. We are more interested to put the desired degree distribution. And then, okay, we just, as a consequence, we understand if the clustering coefficient is high enough or small enough or something like this, especially when you're considering the large n limit.
Yeah, I just thought that's, well, the reason I asked this question is that if you mentioned that there is this like original version of the model which doesn't consider spatial structure. I was wondering, like in reference to that, or with respect to that model, how
Yeah, this one.
different this, like, yeah, exactly.
Yes.
Difference with
If yeah, for instance, indeed, here clustering coefficient should be. I feel like this should be very small, because you can have a lot of edges, but actually you have also a lot of clicks in the structure. So okay, I'm not sure about this. So I don't want to say something wrong. Maybe someone in the audience knows better than me. So I really don't want to go into something I don't know. But there is a very deep difference in this between this model and our model. And it's also the reason why we decided to introduce our model. And the main difference is this one. In this random intersection graph, you cannot share typically more than one group with someone else. Whereas in I mean, if you want to model a real network, real networks often show you that people share multiple interests together. They visit same places, or something like this. So that's the main difference. But in terms of clustering, yeah, I'm not sure to what extent it's gonna be different.
I might a little bit disagree with this bullet in the sense that that's correct if you are in the bounded degree regime, but thinking about more denser graph regimes, so then actually it could happen that you show more.
Yes, this is
Yes,
correct.
for epidemics percolation, this is of course the interesting regime.
Yes, okay, exactly. Yeah.
Suppose the network is sparse enough, I guess, right?
And sparse enough to have a bounded degree.
Yeah.
Yes, yeah, exactly. I was a little bit sloppy there. I'm considering the sparse regime, not the dense regime. Otherwise, it wouldn't make sense to also just to compare the different models.
I have 2 comments and 2 questions. I don't know if I have time to do them all, but maybe
Sure.
one is that I think it's also you can view this spatial hypergraph and maybe like as an advertisement. So I might recommend to kind of check the hypergraph literature also, that because there are people who work on those, and this is very natural model for spatial hypergraphs. So I very much like the model. Then let's see what I was thinking. So actually, in a little bit denser, the connectivity question might be interesting, or I don't know if you think if it's interesting at all, but asking if is this what you get, is it fully connected? I don't know if you thought about this, or is it an interesting question?
Fully connected, I think that's really too much, because, well, okay, first of all, it makes a difference when you are considering the entire plane or the entire space, let's say, so the infinite model, or when you are just considering a fixed setting and then you're taking the large and limit. In our case, I think it is possible to prove that you don't have something fully connected, because in the infinite regime, you can always have some weird individuals that is not connected to any group, even though the connection probability is sufficiently high. So
even though the G is kind of has a very long phase. Okay.
Yeah.
Okay, yeah. Okay.
So that's always going to be the case, unfortunately. That's also going to be a problem, because maybe you want a fully connected graph, especially if you want to do random graphs, random processes on the graph or something. What you can do is just saying, well, let's discard all of them. But the problem, instead of being of how many different components are there, That's also another question
Yeah, sure.
that is actually a question contained in the fact that the graph is fully connected. And the idea is that from what we observed from the simulations, it looks like that when you have percolation, typically you are gonna cover everything really with the largest component. But this is not something that is possible to prove. So it looks like there is really a sharp distinction between something that it's a lot of small communities or a lot of small components and a really huge component that is basically everything. It's not just a big proportion, but really everything. But we can prove this.
Final comment if I may. So
We have
Well,
1 minute.
for this degree distribution, so maybe this technique, we work with Mindagas glossaries, we work with this kind of tuning the degree distribution or calculating the power load. Maybe the same is kind of doable here as well, like exactly kind of finding out the mixed Poisson. I don't know if you tried that.
Yes, we didn't try that. The reason is that we felt like computation were going to be much more involved. But yeah, I have no clue actually if there is some approach to extract, because I'm pretty much familiar with other kind of models where you have hidden variables like some degrees, some weights. So you put expected degrees on the individuals, and then you connect according to some kernel function, maybe like Chung-Lu models or something like that. And there, I'm pretty much familiar with how to retrieve the mixed Poisson distribution for degrees. In this case, I feel like it is more difficult, and the reason is that if a degree is present, you really need to take care of where is the if an edge between individuals is present, you really need to consider to which group are they connecting, because that group is gonna be irrelevant for the.
So then it's a nice future problem, I think. Yeah. Yeah.
Thank you, Riccardo. We
No
have
problem,
to leave
thank
the
you.
room, but we may be in touch.
Yes,
A
sure.
very nice talk. So thanks again.
Thank you. Thank you also for the questions and for
And
your
see you.
patience.
Ciao.
Ciao. Ciao, ciao.
Thank you.